In this video, I would like to show you some examples of calculating the magnetic force on an electric charge. So it turns out it's really easy if the motion of the charge, that is the velocity of the charge, is perpendicular to the magnetic field, right? The magnetic field itself is a vector. So when the velocity of the charge is perpendicular to the magnetic field, the force law is really easy actually. So here I'm going to show you, right, so the force law, the magnetic force, is you take the charge of the object, you multiply by the velocity of the object, but you have to remember that you're going to take the vector cross product with the magnetic field that our charge is moving through. All right, so here's the force law. The vector cross product, this thing right here, sometimes you just care about the magnitude. So the magnitude of the force vector, that's just the strength of the magnetic force. So I'm not worried about the direction of it right now, but it's just going to be equal to the magnitude of the charge times the magnitude of the velocity, right? That's the speed, times the strength of the magnetic field where the charge is. So that's just some number of Tesla, right? But then you multiply by the sine of an angle theta, where theta is the angle between directions of the velocity and the magnetic field. So if the velocity is perpendicular to the magnetic field, what this implies is that, for example, if the velocity is this way and the magnetic field is this way, and there is a right angle between, right? That's how the velocity and the momentum can be perpendicular, is if there's a 90-degree angle between the directions of the motion of our little charge. So here's our little charge Q, and it's moving with this velocity V, whatever that is, and the magnetic field at the location of the charge is this direction, some number of Tesla in this sort of down to the right direction, right? So if V is perpendicular to B, then what that means is theta is 90 degrees, and the sine of 90 degrees is 1. So we're going to put in 1 for the sine of the angle when the motion of the charge is perpendicular to the magnetic field. That's sort of the simplest case, right? So it's the easiest. So, for example, what if we know that an electron is moving with speed, let's say 1,000 meters per second, right? So we'll imagine an electron moving really, really fast in the z direction, right? So I just described the speed and the direction of the motion. So I have described to you the velocity. So an electron is moving with speed 1,000 meters per second in the z direction, and the magnetic field is 5 Tesla, which turns out to be a really, really strong magnetic field. So way, way stronger than the Earth's magnetic field at the surface of the Earth that people use to navigate by with a compass, right? So way, way stronger than Earth's magnetic field. But we're talking about some strong 5 Tesla field in the negative x direction, right? So we'll say that the motion is in the plus z, and the magnetic field is 5 Tesla in the negative x direction. So that means, right, the velocity, we can, so just from this given information, we can infer the velocity. The velocity is 1,000 meters per second. In the positive z direction, we call that k hat, right? So it's 1,000 meters per second in the k hat direction. The magnetic field is 5 Tesla strong, right? So it's some number of the SI unit of magnetic field in the Tesla, and then it's in the negative x direction. So we say that that's a negative 5 Tesla in the I hat direction field, right? It's multiplied. But Q, I have to be careful, is negative E, right? That's the charge of an electron. It comes with this minus sign. Or in SI units, it's negative 1.6 times 10 to the minus 19 Coulomb. But the electron is negative, so I put in the minus sign, right? So the force, the vector magnetic force that's acting on the charge Q is equal to, right, it's Q V cross B. And we're going to put in, so it'll be negative 1.6 times 10 to the minus 19 coulombs. That's the charge, Q. The velocity is 1,000 meters per second, but it's in the k hat direction, right? K hat. And then, so that's the velocity. And there's a vector cross product with the magnetic field strength, which is negative 5 Tesla in the I hat direction, right? So I told you that this process of calculating the force is easy when the angle is 90 degrees, and the angle between k hat and I hat is 90 degrees, right? Because the x direction and the z direction are perpendicular to each other. So it's really easy to calculate the magnitude of the magnetic force acting on our charge Q. So let's calculate that first. So the magnitude, right, you essentially drop, because of all these absolute value bars, right, you drop the SIGN. You're going to drop all these minus signs. So there's 2 minus signs that actually product against each other to be a plus sign. So, but anyways, so it'll be, I'll take the magnitude of the charge, so 1.6 times 10 to the minus 19 coulombs. And then I'll take the speed, magnitude of the velocity is the speed, so it's 10 cubed, right? That's 1,000 meters per second. And then I'll take the magnitude of the magnetic field, 5 Tesla, right? And so we can just calculate this out, right? So there's 5,000, or let's go 10 to the minus 19 and 10 to the positive 3. That's 10 to the negative 16. So it's 1.6 times 5, right? 10 to the minus 16. So that's the 10 to the third times 10 to the minus 19. So that's everything. And then I have Tesla meter per second Coulomb, right? So 5 times 1.6. So 5 times 0.6 is 3. Right, 5 times 6 is 30, so 5 times 0.6 is 3. And 5 times 1 is 5, so that's 8. 5 times 1.6 is 8. And then the Tesla, you'll recall I defined it for you up here. Oh, in the previous video I defined it. It's the, so the Tesla was the Newton times the second times the, or divided by the Coulomb meter. And then I have meters per second times coulombs. That's what's left over. So right here, everything in the parentheses is the Tesla. And you can see that what's the only thing left over is the Newton, right? Because the seconds cancel, the meters cancel, the coulombs cancel. So this is 8, it's about 8 times 10 to the minus 16 newtons. And I told you that a 5 Tesla field is very, very strong. And it is really, really strong. because this is going to give an acceleration, if you think about it, right? The net force on an object equals mass times acceleration. So if I want to solve for the acceleration, right, then all I need to do is, the acceleration is, you take the force divided by the mass. Here's the force, 8 times 10 to the minus 16 newtons. And I'm going to divide by the mass of the, what particle are we talking about? The electron. So the electron has a really, really small mass. I can't remember it off the top of my head, but it's about 10 to the minus 30th kilograms. So if you look at this, right, this is roughly, so 8 is basically 10. So it's 10 times 10 to the minus 16 is 10 to the minus 15. So very roughly speaking, right? 10 to the minus 15 over 10 to the minus 30 is 10 to the positive 15. And the units, newtons per kilogram, right? Don't forget to carry the units along, is meters per second squared, right? It's units of acceleration. SI, because Newton is SI unit of force. Kilogram is SI unit of mass. So 10 to the positive 15 meters per second squared. That's the sense in which that's the sense that I'm talking about a 5 Tesla field being crazy strong, because an electron has an acceleration of 10 to the 15th meters per second squared, right? But directions are important. Directions are really important. So everything that I just showed you how to do was in the lucky coincidence case of 90 degrees, but still, we only ever calculated the magnitude of the force. We dropped the direction, but directions are really important. When you do vector cross products, vector cross product directions are governed by what's called a right-hand rule. So you're going to see right-hand rule explained or maybe sometimes symbolized by RHR. But the right-hand rule is a skill that you need to develop. Right? And your book, any book that describes magnetism and magnetic force with vectors, any book is going to show you very carefully how to use a right-hand rule. So I can't draw well enough, and I'm not videoing my hand to show you doing the right-hand rule. But it is a skill that you need to develop, and you can learn this on your own, but you have to go look in a book, right? You have to learn this on your own. Yeah, if you're in my class, you can just write me a note, and then we can meet on Zoom, and I will show you how to use the right-hand rule if you can't figure it out. But I swear, if you give yourself 15 solid, careful, concentrated minutes of actually trying to do this, y'all are all smart enough to learn this on your own. So it is a skill you need to develop. Really quick though, I'm going to show you something that actually does depend on the right-hand rule, but it doesn't sort of feel like it does. So let me show you some stuff. So cross products between unit vectors. right? So, for example, I hat cross j hat. What is this? So the way that you imagine doing this, let me just actually tell you the answer. I hat cross j hat is k hat. J hat cross k hat equals I hat. And k hat cross I hat equals j hat. Can you see the cyclicity? So I cross j is k, and then what you do is you sort of slide the j, the k against the j on the right hand side, and put the I over on the right. So jk is I, and ki is j, right, for the cross product. Another thing that's generically true is if you take any vector A and you vector cross product with any other vector B, it's always equal to the opposite of the vectors crossed in the opposite order. So this is called anti-symmetric. So this is also just a generic truth about cross products. So notice that A and B aren't necessarily unit vectors, although it is true with unit vectors as well. For example, I hat cross j hat is equal to k hat, and j hat cross I hat, right? You see I just switched the order, is equal to negative k hat, right? So it's a truism for unit vectors, but it's just generically true for any vector, A and B. But right here, these are the cross products for the unit vectors. Ij is k, jk is I, ki is j. So there's a cyclicity, and then you can use this anti-symmetry property to figure out what they are in reverse. So ji is negative k, for example. Okay, so if I go and I look at my original problem, I had the velocity was 1,000 meters per second, and I can't remember, what did we say? So the velocity was 1,000 meters per second in the z direction. Positive z is k hat. And the magnetic field was 5 Tesla in the negative I hat, or negative 5 Tesla I hat, right? So this was my 2 pieces of information, and then I had the charge was an electron, so negative E, or negative 1.6 times 10 to the minus 19 coulombs. And now, if I want to calculate the force, I can actually calculate the force vector. This is the force by the magnetic field on my little moving electric charge. And it's equal to, right, it's minus E. That's the charge. So I'm not going to do any of these magnitudes, right? Because I want to calculate the vector. So I'm not going to do any magnitude stuff. So I'm just going to take all the values. So very carefully, right? The force law, let me put it here. The force law is carefully written. You put V first and the magnetic field second. And because of this anti-symmetry property, putting the magnetic field first is wrong, because this is true here, right? So this is actually, there's nothing wrong with anything that I wrote here, but the mistake would be if you put the magnetic field first and the velocity second, but forgot the minus sign. This is no longer true. What is true is with the minus sign. Okay. So I've got the negative E, that's the charge. I have the velocity, it's 10 raised to the third power meters per second k hat. And I take this thing and I vector cross product with the magnetic field second. So -5 Tesla I hat. So I can collect the minus signs, no problem. I'll just put the minus and the minus together. That's a plus. So I get E times 10 to the 3 meters per second. And then I've already dealt with that minus, so I'll take the 5 Tesla. That's just a number. I'll just multiply over on the 10 cubed meters per second. So everything up front, right? And the only thing left over is K hat is on the left side of the cross. I hat is on the right side, so I have to leave it there. So I've got this, right? K hat cross I hat. And this is equal to the charge of the fundamental charge, E, times 10 cubed meters per second, 5 Tesla, right? All multiplied. And then let me look at my chart. K cross I. K cross I is J, right? So the vector force on Q by the magnetic field B is whatever this calculates out to be, which actually we calculated up here. It was 8 times 10 to the minus 16 newtons, so almost 10 to the negative 15 newtons, right? But it's actually in the J hat direction. So here is the Z direction. This right here, I'll say is the X direction. So the only thing that can be in this direction is the Y direction. And I have an electron, right? So remember that the magnetic field is in the negative I hat direction. So let me draw the magnetic field vector arrow. It's in the negative I direction, right? So that's the magnetic field. And the velocity is in the K hat direction. So that's the Z direction. So actually, let me change color. So the velocity is this way. And it turned out that our force, right? So the force here, let's draw the force in purple maybe. So the force was in the J hat direction. So J is this way. So that would have been the force on our little charge. When you look and you use the right hand rule, right? Because that's something you learned, right? If you look at V cross B, V cross B actually points this way. So why is the force in the opposite direction to the answer to V cross B? The answer is because we multiplied by negative E, right? And the negative sign gives us the opposite direction. So V cross B with the right hand rule is actually going to point in the negative J hat, negative y-axis direction. But because we're talking about a negative charge feels the opposite direction force compared to a positive charge. So this is the force on a negative charge. It points backwards to the direction of V cross B. Okay, so yeah. Let me show you something else. So here is a generic vector fact. If you can do the following thing. Let's say that you have a vector, which is A plus B plus C. So I imagine a vector. And I want a cross product with a vector D, right? So actually, let me make it a little bit more interesting. How about D plus G? So I have A plus B plus C cross product with a fourth vector and a fifth vector. You see there's 5 vectors total. And I want to know what this is. It's equal to the result of a distributive property, right? A FOIL style action with your mathematics, but you have to keep the order. So what that means is A is on the left side of the cross product compared to D, for example. So I'm going to go A cross D plus A cross G plus B cross D plus B cross G. Everything is a vector plus C cross D plus C cross G. And notice that I kept the order. The order is important because if you don't keep the order, you start introducing minus signs, and it's because you lost focus, you lost your organization, right? So you got to remain focused, remain organized on your piece of paper you're doing your work on. And you can do the distributive property with the cross product and vectors, but you must keep the order, or else you'll start getting the wrong signs, right? And in this case, you could imagine that what if you wanted to calculate F equals Q V cross B, but V was actually a multidimensional vector. So that what I'm trying to say is, what if it was twice I hat plus 4j hat meters per second, and the magnetic field was represented by, say, was actually 3D. So 1 in the I hat minus 2 in the j hat minus 4 in the k hat Tesla. Can you see that you're going to have to do a distributive thing? So you already know the rules for cross products. I cross j is k, j cross k is I, k cross I is j. And if you flip the order anywhere, you get minus signs. It's antisymmetric. So you can just use the distributive property. So for example, V cross B is equal to twice I hat plus 4j hat, vector cross product. Actually, let me make that a little clearer. With I hat minus 2j hat, whoops, minus 4k hat, right? And it's meters per second times Tesla. So the cross product, remember you have to keep the order. So twice I hat stays on the left, I hat stays on the right. So I've got twice I hat cross I hat, right? And then I've got 2 times negative 2, so that's negative 4. I hat cross j hat. And then I've got negative 8, so minus 8. I hat cross k hat. So I'm going to put these in parentheses. I've got a lot of terms. And then I got 4j hat times I hat, so cross I hat. And then I've got negative 8, j hat cross j hat. And then I've got negative 16, right? J hat cross K hat. Close parentheses, the units are meters per second times Tesla, right? And then I'll just continue on. So here's an interesting fact. Whenever you have a vector and you vector cross product with another vector, or the same vector, what this is, right, is if you think about the magnitude of it, it's the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between the two vectors. But if it's the same vector, then a vector is parallel to itself. So the angle between a vector and itself is 0, but the sine of 0 is 0, right? The sine of 0 is 0, so the whole thing is 0. You take any vector, if you cross against itself, you will only ever get 0. So check it out. Can you see that that happens in what I'm showing you right now? I cross I is 0. J cross J is 0. But when the two vectors are not the same, right, that is, there is an angle between them, then you're going to have answers, right, non-zero values. So I cross J, if you go and you look up here, I cross J is K with a plus sign. So I'm going to take I cross J and understand it as K hat. I cross K is actually negative J hat. J cross I is negative K hat. And J cross K is actually positive I hat. So if you pay attention to all the signs, right, you see how careful I'm being. It's negative 4 K hat, right? There's a negative J hat and a negative 8, right? That's a plus 8 J hat. And then here is, there's actually a plus sign understood here. So it's negative 4 K hat. So I've got another one. There's two of them. And then I've got an I hat. So negative 16 I hat. And the units are still meters per second Tesla. And if you finish this out, I've got collect all the K hats together. So negative 8 K hat. I've got a positive 8 J hat. And a negative 16 I hat. Meters per second Tesla. So I've calculated V cross B just using the distributive property, and I used this chart up here. Okay, so what I've shown you how to do is calculate magnetic force. I alluded to the right-hand rule, and you must learn this, right? And I told you to go look in a book for it, and you have to do this, right? You can learn something on your own. You should do that. Please don't let this go by without learning.